Now that we've defined the derivative, let's look at some examples. We're going to start off looking at some simple examples about how to calculate the derivative, and this is going to lead you up to doing the IXL where you're going to be calculating these yourself. All right, so here's the definition of the derivative that we set up in the last video. And so the problem that we're going to look at this time is we're going to look at this function f of x is equal to 3. So this is one of the constant functions. So no matter what our input is, our output is 3. And we want to know what is the derivative of this constant function when the x value is equal to 1. All right, so let's try doing this with each one of our two definitions, and we can see that we get the same answer for each of them. All right, so the first one, f prime of 1, we're going to take this definition where a is equal to 1. It's equal to the limit as x approaches 1 of f of x minus f of 1 over x minus 1. All right, so our first problem here is to evaluate the limit, or sorry, evaluate the function at those two values. So f of x is equal to 3. And what is f of 1 equal to? When you put 1 into this function, what is the output? Well, we substitute 1 in for x, but there is no x here. So when x is equal to 1, 3 is equal to 3. 3 is equal to 3 no matter what x is. So f of 1 is equal to 3 over x minus 1. All right, so that's easy enough to simplify the numerator. The limit as x approaches 1, 3 minus 3 is 0 over x minus 1. And let's think about whether we can evaluate this limit. So if we substitute 1 in for this, we get 0 over 0, so that doesn't work. But let's think about what this is actually doing. When x approaches 1, x is never equal to 1. So this thing in the denominator is never equal to 0. So we're never really dividing 0 by 0. And 0 divided by any number that's not 0 is equal to 0. All right, so what we see is that the limit of this function, the limit of this quotient, which is the derivative of f at 1, is equal to 0. Let's try doing the same problem, except with the second definition. So this f prime of 1 is equal to the limit as h approaches 0 of f of, instead of writing 1 plus h, I'll just write it as h plus 1 instead, minus f of 1 all over h. Once again, I want to evaluate this function at these two values. But this is a constant function. So the output is going to be 3 no matter what the input is. So once again, the numerator is going to be 3 minus 3 over h. Limit as h approaches 0. Once again, this is 0 over h. And once again, we are dividing 0 by a number that approaches but never reaches 0. So 0 divided by any number that's not 0 is equal to 0. All right, so what we can see is that calculating this derivative using either of those definitions, we come up with a derivative of 0 using either of those techniques. So what we'll see in a future video is that this isn't, well, it certainly isn't a coincidence that we get the same answer from either technique. What also isn't a coincidence is that the derivative of a constant function is going to be equal to 0. We'll think in a couple video time of why we would expect that to be the case. Once we get to the point where we're not calculating derivatives, but kind of anticipating what they're going to be without doing algebra like this. So that'll be something in the future.